MRI stands for magnetic resonance imaging. It is a medical imaging technique used in radiology to form picture of the anatomy and the physiological process of the body. MRI scanner use strong magnetic fields, magnetic field gradient, and radio wave to generate image of the organ in the body. Magnetic resonance imaging is based on the physics principle of nuclear magnetic resonance or NMR. First described in 1930s and 40s by Isidore Rabi, and he won a Nobel Prize in Physics for his work in 1944. The first inventor of MRI is Raymond Damadian, and the first magnetic resonance imaging MRI exam on a live human patient was performed in 1977. The basic principle of NMR deal with the interaction of certain atomic nuclei, radio frequency energy, and a strong magnetic field.
The definition of radio frequency energy is part of the electromagnetic spectrum that include visible light and X-ray. The radio frequency are at the far left of the spectrum, visible light in the middle, and X-ray to the right. All of these waves are defined by wavelength and frequency. The wavelength is the distance between peak of the wave, and the frequency is how many cycles that the wave complete every second. The amplitude is the height or power of the wave. When we talking about two or more waves, we can also describe phase. The blue and the orange wave have the same frequency and line up completely, so they are in phase. If we shift the orange wave to the right, the frequencies remain the same, but the waves are now out of phase or have been phase shifted. On the other hand, these two waves have different frequencies but start at the same time, so they are in phase. An NMR or MRI radio frequency signal will be described by their unique phase in frequency. Electromagnet can be created by wrapping a wire around an iron nail and running current through the wire. The electric field in the wire coil creates a magnetic field around the nail. The basic principle of electromagnetism, where a flowing current of electron has an associated magnetic field oriented 90 degrees from the direction of the current flow. The battery pushes the electron around the wire. We call the wire to add up all those little magnetic moments and add the steel nail to conduct the magnetic field to object we want to pick up. The direction of magnetic field associated with the coil is defined by the right hand rule curl. The finger of your right hand in the direction of the current flow to the coil, your outstretched thumb will point in the direction of associated magnetic field.
MRI relies on the magnetic properties of hydrogen atoms to produce image. Our body is made up of 70% of water, which is 2 hydrogen atoms for every oxygen. The hydrogen nucleus is composed of a single proton with no neutrons. As a spinning charged particle, this produces a magnetic field called a magnetic moment. The proton is positively charged. If we curl our finger in the direction of rotation, our thumb will point in the direction of the small magnetic field associated with each and every one of the hydrogen protons or spins in our body. The main components of the MRI system include the primary magnet, gradient magnets, radio frequency coils, and the computer. As for the primary magnet used in MRI is superconducting magnet. Superconductive MRI magnets use a solenoid-shaped coil. The person to be scanned will be placed into a large magnet. This magnet consists of coils of wire like this schematic of an electromagnet. The magnets used for medical imaging typically have a strength of 1.5 to 3 Tesla. This is about 300 times as bar magnet. It consists of about 200 kilometers of wire and weighs about 10 tons. The wire used in MRI is the superconducting, meaning the wire has no resistance as long as it is kept very cold. MRIs are cooled with liquid helium at 10 Kelvin on about minus 270 degrees Celsius. In addition, because the wires are superconducting, the current flows through these wires even without applying any external power. As a result, the MRI magnet is always on.
Next is the radio frequency coil. The radio frequency coils are used for transmitting the radio frequency pulse and receiving signals in MRI. The way to detect this small magnetization is by using radio waves and a phenomenon called resonance. A radio wave is sent into the part of the body we wish to scan using a radio frequency coil. These coils can appear in various shapes and sizes. When a radio wave of a specific frequency is sent into the body, the magnetization is tipped away from being aligned with the main magnetic field. The frequency of the radio wave is necessary to tip the magnetization same as the precession frequency of the spins. This is why we call it magnetic resonance imaging. The radio wave is then turned off and the magnetization process resumes by rotating around the direction of the main magnetic field. This rotating magnetization can induce current in a coil of wire or antenna. In other words, the processing magnetization generates a radio wave which could be detected using a radio frequency coil. The received radio frequency coil can be either the same coil that we use for sending in the radio wave or a different one. The amplitude of this radio wave tells us about the amount of magnetization and also the amount of hydrogen protons or water in the body part we are scanning. Next is the gradient magnets, or also called gradient coil. Gradient coil is used to localize the radio frequency signal in space. The gradient coils allows us to know exactly where the radio frequency signals are coming from within the bore and produce 3D images of tissue. But they are also used to provide different contrasts such as diffusion or flow imaging. There are 3 gradient coils which are named according to the axis along which they act. Gradient magnets alters the strength of primary magnetic field, thereby changing the precession frequencies between slices. This can then be used for slice selection and localization in the X, Y, and Z axis called spatial encoding of MRI images. The Z gradient runs along the long axis to produce axial images. The Y gradient runs along the vertical axis to produce coronal images, and the X gradient runs along the horizontal axis to produce sagittal images.
Okay, now let us talk about the relaxation. The radio frequency is used to receive signals to create images, as protons resume their normal state in the primary magnetic field prior to transmission of the RF pulse. This is called relaxation. Relaxation in the longitudinal axis is T1 relaxation, while relaxation in the transverse axis is T2 relaxation. At T1 relaxation, after the RF pulse, several protons flip back to their low energy state parallel to the magnetic field Z axis, giving up their energy to the surroundings, which is the lattice. This results in changes to the longitudinal relaxation known as T1 relaxation or spin lattice relaxation. On a plot of magnetization over time, magnetization increases with time. The T1 relaxation time will vary depending on tissue composition and structure. For example, water molecules move rapidly and do not move into the lower energy state quickly. At T2 relaxation, after the RF pulse, protons that were in phase begin to dephase in the transverse XY axis. This is known as spin-spin relaxation. This results in a reduction in transverse magnetization. Plotting transverse magnetization in the XY plane versus time transverse magnetization decreases over time. In reality, the spins dephase much quicker than T2 because of inhomogeneity in the magnetic field B. Note: T2 relaxation times vary between tissues. For example, water molecules move quickly and as a result, there is less field inhomogeneity.
In summary, MRI image is formed by 3 basic steps. First, we put the person into a strong magnet. This aligns the nucleic certain atom, particularly hydrogen bound in the form of water, with the magnetic field, then sent into a radio wave. This perturbs the alignment of the spin, and as the spin realign themselves with the magnetic field. Thirdly is applying magnetic field gradient to encode the spatial position into the frequency of the radio wave. This allows to determine where the spin are located. The signal we measure then tell us about the amount of the water in different part of the image. For instance, the human brain. Thus, MRI have an ability to see such striking detail in contrast, as well as the ability to see blood flow and oxygenation change related to variation in brain activity. This is what makes MRI the powerful technique today. Thank you.